Welcome to EDU World Space.
Here we're going to look at a few transitions in the hydrogen atom and what types of photons we would expect the hydrogen atom to emit for these transitions. So we're going to start with the Bohr model, which has some simple things such as centripetal force, circular motion, conservation of energy, and quantized angular momentum to develop an expression for the energy levels, quantized energy levels within hydrogen. And those levels are given by minus 13.6 electron volts over n squared. N is the quantum number, sometimes called the shell number, or principal quantum number, because it defines the energy. And I do note that these are negative energies because the electron is bound inside the atom. But what we're going to look at is all possible transitions between the first three levels. And I showed the levels. They actually start out very highly spaced and they get closer together as you approach 0 volts. So the largest energy difference is between N1 and N3, and we'll call that transition A. The next one is between N2 and N1, and we'll call that B. And the lowest energy transition is between N3 and 2. We'll call that C. So let's look at some examples for finding the energy of the photon. The photon basically has to conserve the energy lost by the electron as it transitions. So here we're talking about emission. But the same will be true for absorption. If the electron is raised up by energy, that energy is coming from the photon. So let's see. We're going to take an absolute value here of N3 energy minus energy 1. So that's 13.6 minus 1.5 EB. And that is 12.09 EB. So here we're going to use the energy relationship between the wavelength of the photon and the energy. And we'll use our atomic units so that we come up with the wavelength in nanometers. And pretty simple to work out the wavelength. It winds up to be 102, roughly. We'll say 102.6. We'll say 103. Keep it 2, 3 sig figs. And that is in the ultraviolet part of the spectrum. Okay, B, we're going to take the difference in energy between, let's see, we're doing 2 minus 3. 2 minus 1, sorry. And 2 is 3.40. And likewise, we can find the wavelength. Okay, and solve for the wavelength. Another ultraviolet wavelength. And finally, C. So that is the smallest difference, and it will be the longest wavelength. And again, finding the wavelength. And that gives us a wavelength in the visible region. And in fact, it is the red part of the visible spectrum. That line, by the way, is the strongest visible wavelength of the hydrogen spectrum. And for that reason, it is called the hydrogen alpha line. It's very intense, the most intense, brightest line in the visible part of the spectrum.